Hello and welcome back to the second part of the network information hiding class. This is a brief session. I will discuss local host covert channels that do not exploit network capabilities. So this is a minor topic in this course, but I wanted to at least cover it a bit for completion so that you have a full picture or so that you have a good overview of this whole information hiding and covert channel topic. Such covert channels that are locally realized can exploit several capabilities of the system, usually hardware capabilities or operating system related metadata. If we consider two processes, P1 and P2, and let's say they run within the same environment, that could be the same operating system, two processes on the same operating system. And several covert channels between these processes are imaginable. For instance, P1 could perform some intensive computations or not to signal a 1 or a 0 bit to the other process P2, who has to measure the CPU load constantly. Another example would be if P1 stops its operation at a given time T1 or at a given time T2 to signal a secret 0 or 1 bit respectively, while again P2 has to monitor the process table the whole time. And another option would be if P1 either creates or does not create an entry in the file system. So one file that is known by P1 and P2. They have to agree in advance on this file name, and P1 constantly checks for the existence of this file name. And if the file is present, then let's say it's a 0, and if it's not present, then it's a 1 bit. And P1 and P2 perform this operation, let's say every second or something like that. So they could signal 1 bit, 1 secret bit per second. And these simple examples reveal that covert channels are usually not noise-free because other processes, for instance, could also create the same file. Or there could be delay due to scheduling. Or in the first example, using the CPU load, other processes could also influence the CPU load. Also, it's not clear when a transmission starts or ends. So it would be good if there would be a protocol that signals such meta information. It would also be good to detect errors, for instance, using parity bits. I will discuss network-based solutions for part of these issues in the chapter on sophisticated network covert channels, but this is we will first have a few chapters in between, and then I will introduce you to these sophisticated topics. I have found some pretty interesting covert channels for Docker containers. So Docker containers are essentially lightweight virtualization environments. And you can, using Docker, realize isolated processes in the sense that they do not see other processes. And however, one could imagine that such processes that run in isolation cannot communicate with other processes, but that's not true. And the Docker container technology is not resistant against covert channels. Several covert channels are possible, for instance, by signaling data over the globally used memory or by inode exhaustion. And these covert channels, I will only show you a very small subset of the covert channels proposed in the paper by Luo et al. In 2016. But one that I found pretty interesting is the GUM, or globally used memory channel. So if you have Docker containers, then in the Docker containers you always can see the same amount of available memory that is available to the whole system. So the figure 3 taken from the paper by Luo et al. Shows you in the TOP tool that monitors processes the globally available memory, and that's the same value is shown for the host and for the container. So this does not only include the available memory but also the used memory, as well as the free memory. So one can signal a hidden bit in the following way that was proposed by these authors. So as you can see here, the bit would be 1 if the globally used memory modulo 100 minus globally used memory modulo 50 would be 50. And it would be 0 if the globally used memory mod 100 minus globally used memory mod 50 would be 0. This way one can easily transfer some bits in a rather short amount of time, because you can quickly allocate and deallocate memory. However, you also still need to synchronize sender and receiver. Another example of such Covert channels on local hosts are Covert channels for the Android system. So Android was a subject of a plethora of Covert channel research papers. We also wrote one. I will cover a fraction of the Covert channels that we proposed for Android. The goal usually for Android Covert channels is to establish some policy breaking communication between sandboxed apps. So as you can see here, we propose different Covert channels for Android, and they exploit different characteristics of the OS. These Covert channels transfer information from one process to another while the communication wouldn't be allowed. For instance, the screen state. So whether the screen is turned on or off can be used to signal hidden information. Also the task list, meaning that we can check whether a process is present or not. And however, this is work from 2013, so I think some updates will have occurred for the Android OS here, also in terms of required permissions. And also process priority. Processes can have different priorities on Android, and by using a syscall to decrease the priority, another process can notice this, and also this way you can signal hidden information. And I will show you Covert channel number 2 that uses process priority and screen state to signal hidden information. So the scenario is as follows. This was joint work with Jean-François Lalande, and he did most of the work for this paper, so credit goes mostly to him, and he also draw these figures. So the example scenario that we have here is that we have 2 applications and the user installed both of them, and the first app is one that has the permission to contact remote servers. It can use the internet, but it has no access to the contacts. The user did not allow the app to use the contacts. And the second app has contacts, has the permission to read the contacts, but it has no permission to access the internet. I think today all Android applications can access the internet, but I'm not sure. And so the user would assume that his contacts cannot be leaked to the internet because the app that has access to the internet has no access to the contacts, and The app that has access to the contacts has no access to the internet. We have shown that there can be a covert channel between the first and second app, and this way one can leak the contacts to the other app, and that app leaks the data to the internet. An example could be that a user downloads two smart home apps or two fitness apps or something. For instance, in the case of the smart home apps, one could be used for monitoring the energy consumption, and one could be used as an energy advisor or something like that. There are some requirements for the transmission. First of all, the sender and receiver must run simultaneously. The transmission via process priority of the sender needs to be must be feasible, and the transfer process starts when the user turns off the screen. So how are secret bits transferred? Remember, we want to read in the context somehow, and we assumed that app 1, the sender app, read the context already, and now we want to transfer these contacts bitwise to the covert channel receiver, app 2 that leaks it to the internet. And we have two channels, a data channel and a control channel, for which we use the screen state and the priority of the sender. So the screen state, that's the dashed line here, can be on, the screen can be on or off. And the priority of the sender can be P or P-1. Now let's assume the user turns on the screen, and now it turns off the screen. When the screen is turned off by the user, it's a signal that we exploit to indicate the start of a hidden transmission, but only if the process priority was set to P-1. If the process priority is P, which is the standard priority for the process, then we indicate that there's no data available. Now, data is available because the sender set the priority to P-1 and the screen was turned off, so the sending would begin. However, let's assume the user quickly turns on the screen again, leaves not enough time to read the hidden information, to signal the hidden information. And so this can be the transmission process would then be cancelled, because the end of the transmission is indicated by the fact that the process priority goes back to P, as shown by this arrow here. So the user turns on the screen again and then turns off the screen again, or it gets turned on and off automatically because some message was received or a telephone call was received or something like that. And now the screen goes off again, and now the covert receiver measures the time between the screen being turned off and the process priority being set back to P. And this time slot is divided in by T, delta T, and the resulting value represents the hidden symbol. So this is a typical way to indicate a hidden information, because you have to somehow have some coding set up. And here we have, for instance, all the Latin characters of the letters of the alphabet, and say, okay, if in a simple case, one could say that if delta t is 1 second, then an A would be the transfer of a message for 1 second, and a B would be 2 seconds, and C would be 3 seconds, and so on. And of course, you can also perform this bitwise. There is a video available that shows the secret transmission if you click on this link, and you can also find the original slides of the presentation during RS 2013 that I gave in Regensburg. So this is all for this very short local covert channel session. And next time we will discuss fundamental countermeasures that are not specific to the network, but that are also working, or especially working, for local covert channels and also on the source code level.